Now we will discuss the NTU method. NTU stands for number of transfer units. Okay. First of all, we will define effectiveness of an heat exchanger. Effectiveness of a heat exchanger. This is denoted by epsilon, and this is equal to actual heat transfer over maximum possible heat transfer. So, what will be the Q actual can be given as Cc Tc out minus Tc in is equal to Ch Th in minus Th out. Now consider we have two fluids. Let us say hot fluid is flowing through this hot fluid and cold fluid is flowing through the annular area, cold fluid, and heat transfer is from hot fluid to cold fluid or cold fluid to hot fluid, and its hot fluid's initial temperature is Th in and cold fluid initial temperature is Tc in. So the maximum or minimum temperature that a hot fluid can attain, that will be equal to Tc in, and the maximum temperature that a hot fluid or cold fluid can attain, that can be Th in. These values cannot exceed. So the maximum amount of temperature difference, temperature increase or decrease, this can be Th in minus Tc in. And if we have two fluids, the fluid with minimum heat capacity or a specific heat will reach the maximum or minimum temperature first. So Q dot max can be given as C minimum Th in minus Tc in. If Cc is C minimum, then epsilon is given as Tc out minus Tc in upon Th in minus Tc in. If Ch is C minimum, then epsilon is given as Th in minus Th out upon Th in minus Tc in. Now consider a parallel flow heat exchanger. Parallel flow heat exchanger. From the previous analysis, we have derived that Th out minus Tc out divided by Th in minus Tc in is equal to minus UAS upon Cc 1 plus Cc upon Ch. This we have already derived in LMTD method, right? And from equation this one, we can write Th out is equal to Th in minus Cc upon Ch Tc out minus Tc in. If we substitute this value in above equation, substituting in above equation, we will get ln of 1 minus 1 plus Cc upon Ch into Tc out minus Tc in divided by Th in minus Tc in is equal to minus UAS upon Cc 1 plus Cc upon Ch. Now, we know effectiveness is defined as Q dot actual upon Q dot max. This is nothing but Tc out minus Tc in upon C minimum Th in minus Tc in, or we can write this as Tc out minus Tc in upon Th in minus Tc in is equal to epsilon times C minimum upon Cc. Substituting this value in this equation, we will get ln of one minus 1 plus Cc upon Ch epsilon C minimum upon Cc is equal to minus Us upon Cc 1 plus Cc upon Ch. And if we do some algebra, we will get effectiveness of a parallel flow heat exchanger is given as 1 minus exponential of minus UAS upon Cc 1 plus Cc upon Ch upon 1 plus Cc upon Ch into C minimum upon Cc. So, if let's say Cc upon Ch is capital C. This is known as capacity ratio. Okay, and UAS upon C minimum is given as number of transfer units. This one and this one is important. If this is like this, we can write the effectiveness of a parallel flow heat exchanger is 1 minus exponent of minus NTU 1 plus C upon 1 plus C, right? This is the effectiveness of a parallel flow heat exchanger. Similarly, we can derive an equation for a counter flow heat exchanger. Counter flow heat exchanger is equal to 1 minus exponent of minus NTU 1 minus C upon 1 minus C exponent of minus NTU 1 minus C. This is for counter flow heat exchanger. These two are very important. If we observe the effectiveness of parallel flow and counter flow heat exchanger, we will see that first one, effectiveness of an heat exchanger lies between 0 and 1. Effectiveness cannot be greater than 1. The second one, for a given number of transfer units and capacity ratio, counter flow heat exchanger has the highest effectiveness, followed by cross flow heat exchanger, with both fluid unmixed. Or we can write this as effectiveness of counterflow heat exchanger is greater than effectiveness of cross-flow heat exchanger is greater than effectiveness of tube shell heat exchanger is greater than parallel flow heat exchanger. This is the order of effectiveness of different heat exchangers. And third important observation is, for a given NTU, for a given number of transfer unit, epsilon max is equal to 1 for C is equal to 0 and epsilon minimum for C is equal to 1. Here if you say C is equal to 0, in the previous equation if we put this, epsilon max will not be equal to 1. So for epsilon max will occur if capacity ratio is tending to 0, right? That means the maximum one fluid has a heat capacity greater than the other fluid, very larger than the other fluid, right? If we see, C is defined as C minimum upon C maximum. This will tend to 0 if C minimum is very less than C maximum, right? In this situation, effectiveness will be maximum. And if C is equal to C minimum upon C max is tending to 1, in that situation, minimum effectiveness tends to 0. Okay? For a condenser or evaporator, C max tends to infinity. That is, C is equal to C minimum upon C max tends to 0. In this situation, effectiveness epsilon is given as 1 minus exponent of minus number of transfer units. And the last observation that we can make is, larger the NTU or number of transfer units, larger the NTU, larger the heat exchanger, larger the heat exchanger.